You got a spherical balloon. It's being pumped up. You know, when you first start pumping up that balloon, it's deflated at first, and then once you start pushing air into it, the radius starts getting bigger and bigger. It goes from almost 0 to 1 inch to 2 inch pretty quickly. Okay, and this is a 10-foot radius that we're eventually going to be talking about. So we're talking about a huge balloon. But at the very beginning, the rate of change of the radius is faster than later on in the balloon. As far as I can tell, maybe somebody could argue something different, but I don't think so. Once it gets really, really big, you know, you're still pumping in the same amount of volume per time, but the sides aren't expanding as fast because there's more volume to fill as it gets bigger. Anyway, we're dealing with volume of a sphere. So this is just the standard equation for the volume of a sphere. Okay. And so we want to know something about the rate of change with respect to time. Minutes is the units that we're talking about in terms of time. Okay. So how fast is the balloon's radius increasing? We want to take a derivative of this equation with respect to t, a variable that's not clearly expressed here, t, right? The volume depends on time. The radius depends on time. So we take a derivative with respect to t. So we don't know what the volume is, the derivative of the volume is with respect to t. That's why we got to symbolize it with v prime here. Okay, we're taking a derivative not, it's not d dr, it's d dt of the whole thing. So this is where we need that implicit differentiation stuff. The derivative of volume with respect to time is something we don't know, so we'll just symbolize it with v prime. And then this is 4/3 pi. Now the derivative here, we use the power rule. The 3 would come down and multiply, so we'll put it out front here. Gets reduced by 1, but this is not it, okay? We need to multiply this by r prime. Because the derivative of the radius with respect to time is something that we can't label with in terms of t, because they didn't give us any clear function in terms of t. So that's r prime there. Okay, so using implicit differentiation, and I can clean that up a little bit, the derivative of the volume with respect to time is 4 pi r squared r prime. And the part A is asking how fast is the radius increasing? Symbolized, that's r prime. Okay, with calculus notation, the rate of change of something, that's prime, r prime. So we want to know what r prime is. We want to solve for r prime. And we can do that now that we have a formula for r prime. You can plug in 10 for the instantaneous radius, and then the volume, look, this is a measure of volume because it's cubic feet. So we're plugging in 200 pi in for the volume. And then we get 10 for the radius. And now we just have an algebraic equation to solve for r prime. Okay, 10 squared is 100, so this is 400 pi on the left side. And we want to get r prime by itself, so I'm going to divide both sides by 400 pi. So that makes this 400 pi cancel out. The pi's can cancel. 200 divided by 400, that's 1/2. So r prime is 1/2. And the units here, well, let's go back to the units of volume. The units of volume were feet cubed per minute. And so we took a derivative. So now we're talking about how fast the radius is changing. The radius is a one-dimensional measurement, right? So the radius is feet per minute. Does our text even do that? Yeah, it does. Okay, so that's a 1/2 a foot per minute. And how fast is the surface area increasing at that instant? Well, the surface area of a sphere is 4 pi r squared, but do we have enough information? I gotta think about this. Oh, this one's a little tougher because just algebraically, it's the same type of thing calculus-wise, but I'll show you that in just a second. On this one, they gave us a volume. We could plug that in to help us solve a rate of change of the volume. This one, they don't give us a rate of change of the area. I gotta pause and think about that. Okay, I went down a crazy road, but we actually have enough. So you're lucky you didn't have to sit through all that rambling I just did to myself. How fast is the surface area increasing at that instant? We want to know A prime, right? If A represents the surface area, and if we want to know how fast the surface area is increasing, then we want to take a derivative of this equation with respect to that underlying variable time. So we don't know what the derivative of A is with respect to time. So using implicit differentiation, that's A prime. And then when we take a derivative of this side with respect to time, it's the same thing as the last one. we don't know what r is as a function of time. But that 2 can come down and multiply using the power rule, and it gets reduced by 1. And then we take a derivative of the innermost function. The derivative of r with respect to t is something we don't know, right? So it's implicit differentiation, just like probably the first time you did implicit differentiation was you took a derivative with respect to x of y, you got y prime out of it. The derivative with respect to t of r squared is 2r times r prime, which is what I did here. Okay, so that's now we have an equation for what we want. We just have to plug in the numbers. They said at this instant that they were talking about up above, the radius is 10, so we're plugging in 10 here. And then r prime we just solved to be 1/2. And so if you simplify that, 8 times 1/2 is 4. 4 times 10 is 40, so that's 40 pi, it seems.